now it's also my role. I'm very happy to introduce the first series of lectures for the school. As you realize, we'll have the three main topics, and the three main topics are the three main topics of the program. And we decided to invite two people to present to the introduction to these topics. And the first one is operator algebras. It will be done by Hillier from Lancaster and Sergey Neshveyev from Oslo. And it's my great pleasure just to introduce Robin and ask him to start.
Okay. Water. Thank you, Adam. Do I need a microphone, or are these room microphones?
I think they are.
It's okay? Right. Okay, then thank you, Adam, for the introduction, and thanks to the organizers, so Matt, Adam, Christian, and Laura, for organizing this very exciting program, something new, and I'm looking forward to this. And of course, as a first speaker, I also want to thank the Newton Institute for offering this opportunity to us and for providing the facilities and all the support. Okay, then let me begin. So we were asked to speak about operator algebras, and it wasn't quite clear to us what exactly we should cover because it's like a very broad topic. That's why we sent out this questionnaire, which most of you have probably completed. And we identified that it would be a good idea to start with some basics about von Neumann algebras. So I must apologize to those of you who are experts in von Neumann algebras and will find this very boring. So we want to try and find a nice middle way. You can correct all the mistakes. And I want to, we start with von Neumann algebras and work ourselves forward, and would like to end with a Kohn embedding problem, which is like based on von Neumann algebras, and which is a very advanced topic, but in light of the results from a few years ago, thought that could be of interest also as a nice connection point between operator algebras and quantum information. And so I'm going to start, I'm going to give the lectures today and tomorrow, and Sergey will then take over on Wednesday and Thursday. And that's the plan. Okay, then. Okay, so the first thing we want to look at in order to actually define von Neumann algebras are topologies on B of H. Okay, so on B of H, so H is a separable, usually infinite dimensional Hilbert space. Sometimes it could be finite, but for most of what we're doing, it should be infinite. And then on, so we've got a norm that's induced by the inner product on the Hilbert space, and then we can look at the bounded linear operators on this Hilbert space, so from H into H. And we've got a natural topology that is defined by the operator norm. So you have the Hilbert space norm here, and then you look at all xi, so the vectors here, which you apply your element x in the bounded operators, and you take the supremum of all these norms. Okay, and that defines me the operator norm. Now, I would like these to be bounded, of course, if it's a bounded operator. And for the operator norm, I would like them to be uniformly bounded. So if I take the supremum over all of them, I would like to find a uniform bound. Now that's quite a strong assumption, and sometimes one would like to weaken that a little bit. And that leads us to another topology I can introduce now. Okay. So on B of H, let's write that here. So the strong operator topology on B of H is locally convex topology generated by the family of seminorms. And here we use what we've got up there. So we map X to X psi. Okay, so for every vector in the Hilbert space, I get a seminorm by using this definition. So here I have the Hilbert space norm, and then X goes to X psi. This defines a seminorm on B of H. Okay, and the topology is then generated by taking families of seminorms that defines me my basis for neighborhoods around the point, and that generates then the topology. Okay, so that is the one that we have up here. So as you can see, this is a bit weaker than the assumption over there, because here we would like to have all of them bounded, but not necessarily uniformly. While here, over there, we have the supremum, so we want it uniformly bounded. That's a stronger assumption. Okay, I left some space here, because we can vary that a little bit. So this is one other topology, and I'm going to list a few further ones. So here we want to introduce another one, the weak operator topology.
Robin, sorry, I imagine people at the back are probably struggling to see. Do you think you might write a little bit larger?
Shall I write larger? Okay. Okay. I try.
People from the back are very welcome to move to the front if you find it easier.
Are you able to hear me? Yeah, okay. Just writing larger. Okay. Then, so the weak operator topology is the locally convex topology generated by seminorms. So how can we weaken this even further? If we look at the norms x psi, how can we weaken this further? Well, we can look at this one here, where eta and psi are in my Hilbert space. Okay, so that defines me a family. For every vector eta and psi, I get a seminorm this way, and then requiring boundedness of each of them is even weaker than this one, because you get this one by taking like supremum over all the etas, and then you get that one by taking supremum over the xi's, right? So that gives me a very weak one. That's why it's called a weak operator topology. Let me highlight that. And then we can introduce a few other ones. So here we have the strong star operator topology. So again, this is a locally convex topology. I'm not going to write that out again. And here our semi-norms are the following. We take the same as here, as in the strong one, and then we add this term. So why is this relevant? Why is it important to look at the X star here? So if we look at the original norm topology, then this norm has got a C star property. So that means if you take X star, it has the same norm as X. Now, in the weak operator topology, you can do the same. If you take X star, that's the same as putting X here, and then by symmetry, you will get the same semi-norm. Well, not the same, but exchanging eta and psi, you get again a weak semi-norm. All right? And if we do the same thing here, however, with a strong operator topology, that is not the same. Okay, taking norm X star of psi is not the same as norm X psi. We're going to see an example in a minute. And so, in order to remedy this problem, one can look at this combination, norm of X psi and norm X star psi. All right, so this is a bit stronger than what we have here. So that's the strong operator topology generated by these ones here. Okay, then one can introduce a few further ones. So we have the so-called sigma weak, also called ultra weak operator topology. And that's the one generated by the following semi-norms. So we're taking a sequence of vectors in my H. And I want this to be an L2 sequence. I want these eta n's and psi n's squared to converge. So eta n and psi n should be in L2. Okay, so if I take eta n norm, this is now eta n norm squared, and I take the sum of these, that should converge. And then that defines me another semi-norm. Okay, so that's, is the size fine now? Yeah.
Robin, should the absolute values be outside the sum?
Yes. So next 4, 5. So the sigma strong operator topology. Is the one generated. So we do some, like a combination of this one and this one. So we have our X psi n where this is in here. Okay, so I want this sequence here converge, and then the final one, sigma strong star. Just for completeness, we won't need all of them, but it doesn't harm to introduce them. So we have norm xi n squared plus norm x star psi n squared. Okay, so that defines another one. So this gives us 6 other topologies now on B of H. You could cook up even more if you like, but these are the ones that one usually considers. And there's a nice relation between them.
Excuse me? Is there a reason why, for example, in like 5 you put a square root, but like in 4 you don't put a square root, or in 6?
Yeah.
But also like in
It-
the weak versions, is there a reason why you don't put a square root outside?
For the weak one,
Yeah.
well, you don't have, for the weak one, you don't have x squares essentially. Here you have a square, so the x is essentially squared for the norm. That's why I want to have the square root here again.
Like
Actually, we could remove all these square roots, so it doesn't really matter whether you have a square root or not, because if it's bounded with respect to the square root or without the square root, it doesn't change anything.
If you want to do some,
Want the semi-norm, then the reason you gave is the
Yeah, okay. That's true, yeah. So what did I want to say? Yeah, so we want to look at relation between these. So we already saw that like the norm topology is really the finest topology, the strongest one. And then you have, this one is really the weakest, and this is a bit stronger than this one. And we can summarize this as follows. So we have the norm or uniform topology. That is the finest. That's what I try to denote by this sign. This sign will have a different meaning tomorrow or later, but for now it means like finite topology. And the next one that you could consider is this sigma strong star operator topology. Now this is a bit stronger than this one, because here we want continuity with respect to the star operations, which we don't have here. So this gives me something slightly weaker. And then the sigma weak is again weaker than this one. Okay? And then, now if you compare the weak and the sigma weak, for example, then you can see if you just consider the sequence where eta 1 is equal to eta, and eta 2, eta 3, and so on are all 0, and you get this one as a special case of this one. So this is weaker than the sigma weak. So we can write this like that. Now we already saw that the sigma weak is weaker than the strong one. And here we have the star, strong star. And for each of them, the sigma version is finer than the non-sigma version. Okay? So this gives us like an order among these topologies. And so this shows that in general, we could have lots of different topologies. So we don't really know whether this is strictly stronger, strictly weaker than this, or whether it's actually the same. And we want to see that with an example here. So one example.
Can I ask a question? Just as a sanity check, if you're talking about containment of open sets, that goes the other way from this thing?
Containment.
So if you're thinking about as a topology, like the open sets of the weak operator topology are contained in the open sets of the strong.
Yes, the open sets in here are contained in the open sets here. Yes,
So
but this. So I use this to indicate finer. This topology should be finer and this should be rougher. That's why I use this sign. You can introduce whatever sign
got it.
you want. And we're not going to use this sign again after this. So I'm going to wipe this out in a few minutes and then you can forget about it. So, example. Yeah, we could try and come up with sequences that, so we see that this is finer than this one. So if you have a sequence that converges in this topology, then it will also converge in all others. The other way around, if we have something that converges here, it might not converge in all of the other ones. So is this the case? Can we find something? And so I wanted to give you at least one small example. So let our Hilbert space be L2 of n, and S should be the right shift. The right shift operator on L2 of n. So if we have a basis here, say E1, E2, E3, orthonormal basis, then that shifts that E1 to E2, so EJ to EJ plus 1. Okay, that's the right shift. And so it shifts EJ to EJ plus 1, it turns out that this is an isometry. Okay, the kernel is 0. It's an isometry. And S is an isometry. And we define Xn as S to the power of n. So I shift by n steps to the right. And then we see that Xn psi, since this is an isometry, this is equal to psi. But if we take the star, so the adjoint of Xn on psi, so yeah, let's use squares here. So what do we get in this case? So the adjoint of the right shift is the left shift, and so here I just get, so all these entries psi k, and I start summation, so I shift everything towards the left, and so the first n terms drop out, they go to 0, and I start my summation at n plus 1. All right? So that's what I get if I look at the star. And now you already see what I pointed out at the beginning. So here, the norm of x psi is in general different from the norm of x star psi. That's why we want a strong star operator topology. That's the reason for introducing this. So if we let n go to infinity, then this goes to 0. Okay. So we get that x n star so this goes to 0 for every choice of psi, okay, independent of the choice of psi. And that by definition is the strong operator topology. So we can say that x n star converges to 0 in the strong operator topology as n goes to infinity. And okay, and since it converges in the strong operator topology, it must also converge in the weak operator topology. But if we now take the strong star operator topology, strong star operator topology, then what, sorry, xn. So then what happens in the strong star? We have to consider xn star psi plus xn star star. Xn star star was the original xn, and we already found that that's an isometry, so it can't converge. So in the strong operator topology, it doesn't converge to anything. So we found something that converges here and here, but not here. So this can't be an equality. This is finer than this one. Now we can modify this very easily to find something that converges here, but not here, by simply taking xn. So xn xn converges to 0 in the weak operator topology. So you just have the right shift. So something converges in the weak topology if the conjugate, if the adjoint converges in the weak topology. We already found that xn star converges in the weak operator topology, and so xn also converges in the weak operator topology. But xn does not converge in the strong operator topology. So we now got something that converges here, but not here. So that shows these ones. So with a little bit of more work, you can try to find examples for each of them. And so we're not going to do this here, but just as a little illustration. Okay. So this gives us like the differences between these topologies, but there are also some things that they have in common, and that's very important. So if K is a convex subset, and K1 is the unit pole of K. So K1 are all the elements in K, in this convex subset, that have got norm less than 1, like operator norm less than 1. Then the following are equivalent. Let's write 1. A is closed in this sigma weak operator topology, the one over here. K is closed in the sigma strong operator topology. K is closed in the sigma strong star topology. K1, so the bounded elements in K, the ones with norm less than 1 subset is closed in this weak operator topology.
Don't you want, like for 4, 5, and 6, don't you want the subspace? Because it could be that the K does not intersect the unit ball at all.
The subspace, right? Yeah. We need that actually for all R. Sorry, thanks for pointing that out. AR for all R. R should be the R ball. Okay? Yeah, thanks for pointing that out. So that's the equivalent. So that's not an easy theorem. I'm not going to look into the proof. It requires quite a bit of work. But that can be shown, and that's quite useful now, because here they look very different. But if you actually look at convex sets and the closures of convex sets, then they become the same, and that is very nice.
Sorry, just to connect this to my existing knowledge, is this Kaplansky's density theorem?
No, no, not yet. But I think we're going to come there until 10:45, right?
Yes, 10:48.
Then we're not going to come there. So, no theorem. Definition. So, let M be a unital star subalgebra then M is called on Neumann algebra. If M is closed. Okay, so I say for Neumann algebra, it's like a unital star subalgebra of the bounded operators, which is closed with respect to this topology here. Okay, that's what I would like to use as a definition. Now,
Excuse me. Could you remind what unital star subalgebra?
so you have the star operation in here. So the map that takes an operator and gives you the adjoint of the operator, the X star, and so it should be closed under this operation. So for every operator, there should be the corresponding adjoint in there, and it should have a unit. Well, the unit of P of H should be contained in M. Okay. So then another definition, or maybe that's part 1. Part 2, M prime should be all elements in B of H which commute with all the elements in M. So the commutant, so xy equals y, x. So we call that the commutant of M. Okay? So M prime is the commutant of M. So that works for any unital star subalgebra. I can construct the commutant this way. Now, if M is a von Neumann algebra, then we can also define the center of M is defined as follows. I take M and I intersect it with M prime. Can the center be empty? The center cannot be empty because we require this to be unital, and so the unit operator commutes with all the operators, and it's also in M, so it's in M prime, and so the center always contains at least multiples of the unit operator. Okay, and final, that's the center, and again, if M is a von Neumann algebra, then it is called a actor if the center consists just of the multiples of the unit operator. So, okay, is that readable? Okay, now we can come to theorem. Let M be a unital star.
Robin, just be aware that the podium's quite annoying on the side.
Everybody can see it. No, Adam can't see it.
I'm okay.
But everybody else can see it, right? Apart from Adam.
But
That's
maybe
up.
keep pushing it up rather
Yeah,
than
I'm
writing it down.
I'm gonna push up. So let M be a unital star subalgebra. Then, if I take the weak operator closure of M, then I get a von Neumann algebra, obviously by definition. And the nice statement now is the following. So if you take the weak operator closure, that's the same as taking the strong operator theory closure. And actually, it's also the same as taking any of these closures apart from the norm topology. Any of these locally convex closures. And this is equal to the bicommutant of M. And this is called the von Neumann's bicommutant theorem. Okay. So this is very surprising. Does anybody find this surprising? You should find it surprising. Why is it surprising? So well, here we have something that's essentially topological. So we're talking about like topologies, strong, weak operator topologies. That's the left-hand side. On the right-hand side, we have something that's purely algebraic. So in the definition of the commutant, you're not using any topology. You're just looking at like algebraic commutation relation. And to see that these two things actually give you the same is something very surprising. And that's one of the key results about von Neumann algebras. And yeah, so von Neumann proved this. That's why it's called von Neumann's bicommutant theorem. And von Neumann really started all the theory about von Neumann algebras and the initial definition. And that's why they are called like von Neumann algebras. So afterwards, there are lots of other people who made great contributions to that, but that's one of the first steps. He proved the first big theorems. Yeah, and so this is one of the results. I'm not sure whether we can look at the proof. It takes more than 2 minutes. Let's do something else instead. Yeah, let's call it A. Be a unital star subalgebra. Then what can we do? Well, we can look at the weak operator theory closure, which is the same as the bicommutant or any of the other closures over there. And so if we take this one, then we get a von Neumann algebra, and we can look at the unit ball, so all the elements in here which have got norm less than 1. So you see we're always using the norm, not in order to get the topology, but in order to get the size, and that's how we define the unit ball.
Can you define bicommutant?
Bicommutant. Bicommutant, I mean the commutant of the commutant. So this thing here. What is M prime prime? M prime prime is by definition, you take the commutant of M, and then you take the commutant of that again. Always inside this fixed B of H. If you change your Hilbert space, if you embed it into some bigger Hilbert space, then the commutant will change. So it's a von Neumann algebra is always linked to a specific Hilbert space. Okay, we're going to see tomorrow maybe what happens if we look at different Hilbert spaces. So that's how we define the commutant inside this fixed Hilbert space, and then we can take the bicommutant. So what can we notice about the bicommutant actually? What's an immediate result about the bicommutant? Immediate observation. That's a bit...
Contains M?
It contains M, yes. Where do I write that? Let me write it here. Remark, M prime prime contains M. Okay, so this commutant is a little bit like orthogonal complements in a inner product space. So if you start with a space, you take the orthogonal complement and the orthogonal complement of that again, you get something that contains the original one that you started with. So that's the bicommutant. So that is obvious. And so if you start with some algebra M, then in order to get time.
I have a question.
Let me finish my.
So what's this ambient space? Like it's always just B of H? Like
M is inside B of H, yes. So M is a
there
star.
has to be some big space in which you are considering these statements, right? Let's say when you look at this bicommutant.
Yeah, so we
That's
fix.
still the B of H?
Yes. We always have H as a separable Hilbert space, and we want to fix that for now. And then we're looking at subalgebras inside this fixed Hilbert space. So this line, the first line, really is important throughout this talk. These talks, that H is like a fixed separable Hilbert space. And then inside that, I can look at subalgebras. Okay. Yeah. Let me just finish this theorem here. So if you take, I wanted to say, so we know that M is always inside M prime prime. And using this theorem above there, if you want to ask, what is the von Neumann algebra that is generated by some subalgebra, then you could say, well, it should be the smallest algebra that is weakly closed and that contains your original algebra. So it should be the weak operator theory closure of the original algebra. But how to get that? Well, the theorem tells us that we can actually get it by taking the bicommutant of the original algebra. So we don't have to do any topology. We can just take bicommutants, and we automatically get a von Neumann algebra out of that. Okay? So that is why this theorem is really nice. And so another nice theorem that I just only want to write down now is the following. So if you start with A, some unital subalgebra of P of H, and you take the unit ball inside this A, and then you take the closure in actually any of these topologies, then you get the same as first taking the closure in a weak operator topology and then the unit ball. So you can swap these two things. Okay, so that is called Kaplansky's. Someone asked for that previously, so that is Kaplansky's density theorem. Yeah, so that's for the unit ball. You can actually do that for any R ball if you want. And we can also do it for the self-adjoint elements. So what is the self-adjoint element? Well, if it's equal to its adjoint. So in B of H, we know an element is self-adjoint X if X equals X star. And so that notion carries over to von Neumann algebras. And so here, the self-adjoint elements inside this unit of stars of algebras are the ones which are equal to their adjoint. And we have this property. So the self-adjoint elements which have norm less than equal to 1 are exactly the same. Question, why can't I use the double commutant here? Can I replace this closure in weak operator topology by the bicommutant?
Would it give you anything different from just doing a bicommutant? Exactly.
Yeah, so in this case, I will get an algebra. The bicommutant always gives me an algebra, but on the right-hand side, I don't have an algebra. I've just got a subspace. So when we're not talking about algebras, then this is not true, okay? Here, we're always looking at the full algebra, not at subspaces. So if I take the bicommutant here, I get a big algebra, which is necessarily bigger than this one. Contains all the multiples of elements in here. Okay? Right, so that was just a little final question. I think I should stop here, right? I'm already over time. Okay.
Any question at this point?
So the unitality assumption in the definition of the von Neumann algebra, that's just to avoid trivialities. And we could also define it as a...
You could have... Yes, you could do that without the unitality. Yeah, but then you wouldn't have this bicommutant theorem because
That's what we said. You wouldn't have the bicommutant theorem. There's one.
you would have to then look at you could have a maximal projection that gives you everything, and then you have to take the bicommutant theorem on that subspace. That is the subspace of H that is spanned by this M. Where's my chalk? So there would be a projection then that spans this subspace, and if you then work with this Hilbert space, P times H instead of H, and define the commutant with respect to that and the bicommutant, then you will get something similar again. But it's much more convenient to have just unitality.
Okay. Maybe one more question.
I have two really quick questions. Sure. I just couldn't read the bottom there. So you're saying it's a factor if the center is trivial, basically?
Yes.
Okay. And then, was the comment you just made about Kaplansky's density theorem meant to imply that like the proof requires a lot more than just somehow using the above? Like you can't. Yeah. Is the proof involved?
Yes. Yes. It's not straightforward.
You can't just somehow use the above theorem and then do something.
No.
Okay.
It's significantly more involved than so maybe just like one very short. There was somebody from the back.
So you define the von Neumann algebra as being weak operator closed.
Yes.
Is this the same as taking any other topology given your theorem on the left hand side?
Yes, so by this theorem it's at least the same as defining it to be strong operator closed, and one can show that it's the same as closed in any of these topologies. So although they are different in general, but when you look at the closures for these algebras, you get actually the same. Again, that's not obvious, so we can't do that here, but it is the case here.
Sorry, you kind of introduced a ton of different of these topologies. Can you tell me, like, what are the most important ones? Like, I assume this weak operator topology, right? Like, what else is usually used?
I think, like, they're all used sometimes, but like, I think the weak is, let's keep in mind the weak and the strong ones. I forget the other ones for now.
I want the sigma weak. I want the sigma weak as well. The others, don't forget, these three.
The sigma weak, yeah, the sigma weak is interesting from a topological point of view, because if you look at Banach spaces, then the sigma weak topology would be the weak star topology in the sense of duality in Banach spaces. Okay, that's why it is quite important. Yeah.
Okay, and thank you very much for the questions. We'll recommence in 20 minutes. So thank Robin again.